Today we've got an extra special topic for our video. We don't have a section number for this, but we're going to be talking about induction. Mathematical induction is a process or a technique that we use to prove things essentially for all integers by proving only for a couple. This comes in handy for things that depend on the integers. For example, if I'm looking at the sum from I equals 1 up to n of I squared minus I, this is the sum of all terms with the function I squared minus I, where the variable I takes on the value of all integers from 1 up to some higher number n. So for example, if I had the sum I equals 1 up to 5 of I squared minus I, this would be equal to the I equals 1 term, 1 squared minus 1, plus 2 squared minus 2, plus 3 squared minus 3, 4 squared minus 4, and then I stop here at 5 squared minus 5. And I want to add all of these up. And this is kind of tedious. Let's see, I have 1 minus 1, so that's 0. Here I have 4 minus 2. Here I have 9 minus 3. 16 minus 4. And here I have 25 minus 5. Whoops. Come on. 20. And this has a final answer of 40. But this could be a very tedious calculation if I was looking for example, the sum I equals 1 up to 100 of I squared minus I. I would have to write out 100 terms, one for each I from 1 to 100, and then I would have to add all of those up together, and that would suck. But there's actually a formula I can use for this. The sum of I equals 1 up to n of I squared minus I would technically be equal to n times n plus 1 times 2n plus 1 divided by 6 minus n times n plus 1 all over 2. But the question is, how do I verify that this is going to be true? Well, I would have to verify that this is going to be true for every integer n here. I would have to prove that it's true for the sum from 1 to 2. I'd have to prove that it's true for the sum from 1 to 3, and the sum from 1 to 4, and so on, which would take infinitely long because there are infinitely many integers. So let's start off with a simpler version. If I just had the sum from I equals 1 up to n of just I, then this is the sum of the integers from 1 to n. So every integer from 1 to n, this is 1 plus 2 plus 3 plus 4, all the way up until I get to plus n minus 1 plus n. And there's actually more than one way to verify this, a closed formula for this problem. There's a popular story about Friedrich Gauss getting in trouble and being asked to add up all the numbers from 1 to 100 as a punishment, and he comes back in 2 minutes later and he already has the results. And the trick works like this. Suppose I have this sum here. I want the sum from I equals 1 up to n of just I, so I want 1 plus 2 plus 3 all the way up to n. And I'm going to add the sum again to that. So if I add here n plus n minus 1 plus n minus 2, etc., plus 2 plus 1. So I've written my sum twice, once forwards and once backwards. But I'm going to add the terms directly down. So I'm going to have 1 plus n here. I'm going to have 2 plus n minus 1, so that's another n plus 1. 3 plus n minus 2, that's another n plus 1. And that happens for every single pair all the way to the end. I have n minus 1 plus 2. And I have n plus 1 here. So how many n plus 1s have I ended up with by adding this series to itself? Well, for each number here, I went 1, 2, 3, 4, all the way up to n. So I have n times n minus 1. Plus 1, sorry. But this result is also equal to twice the sum from I equals 1 to n of I. So 2 times I equals 1 up to n of I is equal to n times n plus 1. I added it forwards, and then I added it backwards, and I added them both together, which means the sum from I equals 1 up to n of I is equal to n times n plus 1 divided by 2. Which is a neat way to do things, but it's really only a useful technique for this particular sum. It won't help me with the other sum I have up above. It won't help me do the sum of the squares of the integers, and it won't help me solve this equation that I have up top, where the sum of I squared minus I is equal to whatever that is. So for that, I'm going to use induction. And what induction is, it's usually called the principle of mathematical induction. It can be summarized as follows. If it works once, and any time it works the next time, then it works all the time. Which is kind of a funny way to say things, but let me dress it up in terms of the sum of the integers from 1 to n. So I'm going to be using induction to prove that the sum of the integers from 1 to n is equal to n times n plus 1 over 2. And how I do that is I start off with a base case, or a couple of base cases. It's usually better to have more than one, to make sure that it works at least once. So I'm going to do the sum I equals 1 to 1. This is the n equals 1 case, and I'm going to do an n equals 2 case. So the sum from I equals 1 to 1 of I is just 1, and the other side of the formula, I have n times n plus 1 over 2. So I have 1 times 1 plus 1 over 2, but this is 2 divided by 2, so that's equal to 1, so that checks out. But that's kind of a boring sum. So let's try it again with n equals 2. This should be equal to 1 plus 2, which is equal to 3. Versus, if I plug 2 into the other side, I have 2 times 2 plus 1 all over 2. Those cancel, giving me 3. So that also checks out. Now I move on to the other part, the induction step, which is the part that says if it works at least once, then it works the next time. So we'll assume that this formula, with an I, the sum from I equals 1 up to n of just I, is equal to n times n plus 1 over 2 for all n up to a certain integer k. We'll just assume that I've checked up to whatever k is. Then I want to show that it's going to work for k plus 1. So we'll start off with the sum here, I equals 1 up to k plus 1 of I, which is equal to, I can actually split my sum, because this is equal to 1 plus 2 plus 3 plus dot 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 all the way up to k minus 1 plus k plus 1. That's what that means. Parentheses. But this first chunk here, all the way up to k, that's the same thing as the sum from I equals 1 up to k of I, plus the last term I didn't include, plus k plus 1. Now what my assumption says up here is that my formula was true up to k. So that says that the sum from I equals 1 up to k of I, that this is equal to k times k plus 1 divided by 2. I take whatever number's on top and I plug it into the formula on the right. Which means that the sum I equals 1 to k plus 1 of I is now equal to, I'll replace this first sum with k times k plus 1 over 2, and I keep my k plus 1 over here. And I'll play with this and see if I get something that looks like the formula I was supposed to get. So I can factor out a k plus 1, giving me k over 2 plus 1, right? Which is k plus 1 times, I can find a common denominator. I have k over 2 plus 2 over 2, which is equal to k plus 1 times k plus 2 divided by 2, or if I rewrite this as a single fraction, I have k plus 1 times k plus 2 all over 2. Now what was I supposed to get? I'm supposed to get whatever n is. I'm supposed to get n times n plus 1 over 2. So the sum from I equals 1 up to k plus 1 of I was supposed to be equal to k plus 1 times k plus 1 plus 1 all over 2. But that's exactly what I have here. This is k plus 1, k plus 1 plus 1, because 1 plus 1 is 2, all over 2. And that proves what I wanted. Because if I reread this, I assume that the formula works for every integer up to k. In this case, k is whatever base cases I've gone up to. So if I assume that it works for n equals 2, then this work here, k is equal to 2, I've just proven that the formula works for k plus 1, or n equals 3. And if it works for n equals 3, then I run through the induction step again and say, oh, this proves that it's true for 4, which in turn proves that it's true for 5, etc., and it goes on forever. Except I don't have to do it. The proof I've already written does it for me. So I can try this again with the sum I equals 1 up to n of I squared. This is the sum of the squares of the integers from I equals 1 to n. And I'm saying this should be equal to n times n plus 1 times 2n plus 1 all over 6. We'll do some base cases. If n is equal to 1, then the sum from I equals 1 to 1 of I squared is just 1. Versus the other side, I have 1 times n times 1 plus 1 times 2 times 1 plus 1 all over 6, which is equal to 1 times 2 times 3 over 6, which is equal to 1. So that checks out. If I do n equals 2, I'm going to have 1 plus 2 squared, which is 4, so I get 5, versus 2 times 2 plus 1 times 2 times 2 plus 1 all over 6, which is 2 times 3 times 5 all over 6, giving me 5 again. So that checks out. Then I do my induction step. I assume that this formula is true for all n up to a certain integer k. So for all n less than or equal to k. And I'll find out what the sum up to k plus 1 is. And again, this is the same thing as I equals 1 up to k plus the k plus first term, which is just k plus 1 squared. Whoops, I squared. There we go. I've assumed that it works for all n up to k, So I get to say that this sum here is k times k plus 1, 2k plus 1, all over 6, plus k plus 1 squared. And then I just need a common denominator between these two. So let's find out what this looks like. I'll factor off a k plus 1, because that's the best I can do, and see if I can make it look like the formula that I want. I'm going to multiply this out. I'll have 2k squared plus k plus 6k plus 6 all over 6. So this is 2k squared plus 7k plus 6. So can we factor that at all? I think we can. I get 2k and a k. I should have 6 factors of 6, which add up to 7 when I double one of them. So if I do plus 2 and plus 3 like this, I'll have 2k squared plus 4k plus 3k, that makes 7k, plus 2 times 3, which is 6. And again, the formula was supposed to look like this. And I think it still works, because I have a k plus 1 here. If I take 2 away from this 3, so I have k plus 1 for the k plus 2. It's divided by 6, which is good. 2k plus 3 is the same thing as 2 times the quantity k plus 1 plus 1. And that matches up with the formula I was supposed to get up there. Which means, for that original weird series I gave up there, if I equals 1 up to n of I squared minus I, this is actually the same thing as the sum of I squared plus, minus the sum of I, which is equal to n times n plus 1 times 2n plus 1 all over 6 minus n times n plus 1 all over 2. Now, if you really wanted, you could do this with induction separately, but it would involve a little bit more work when you do the induction step. So part of the reason we're talking about this in calculus is these series here, they show up in calculus too. In chapter 11, there are several problems which would need induction to solve, but there are also some exercises here in calculus 1 that we can solve using induction. There's a couple in section 4.3 in particular. There's one here that I like in section 4.2. This is number 21 in section 4.2, and it's actually a proof of the fundamental theorem of algebra, or at least a corollary of it. And the fundamental theorem of algebra, you might recall it vaguely from algebra 1 or 2, is that every polynomial of degree n has at most n roots, or solutions, or zeros, or whatever you want to call them. And it's actually pretty easy to make a polynomial of degree n with exactly n roots, because a root is the same thing as a linear factor. So if I wanted a polynomial of degree 5, for example, with 5 roots, I would just pick 5 roots for this to have. I could have x plus 1 times x minus 1 times x plus 2 times x minus 3. Here I have a total of 5 roots. I have 5 linear factors, and the roots are -1, +1, 0, -2, and +3. But the question is, how do I know I don't have a polynomial with more than n roots, or with more roots than it has degrees? And this is actually true because of Rolle's theorem here in section 4.2. And I'm going to be able to prove this with induction. So I'll set up my base cases. I like to do 2 of them, or more, because sometimes it helps me find out what I'm going to need to do for my induction step. So let's say n equals 1. What I mean by that is the degree of the polynomial is equal to 1. But a polynomial of degree 1 is just a line. So we'll call this my polynomial is equal to a line, but that's mx plus b. And this should have exactly one root, unless the slope is equal to 0. So we'll suppose p of x has more than one root. We'll suppose it has two roots. We've done this before with an example with Rolle's theorem. If I suppose it has more than one root, it has two roots, then I should be able to get some kind of a contradiction using Rolle's theorem. So we'll suppose that it has two roots. Then Rolle's theorem says that there is a slope of 0 somewhere in between the two roots, because f of a equals 0, f of b equals 0. That's equal on the endpoint, so there must be a slope of 0 in between. P prime of x is equal to 0 somewhere between the two roots. But P prime of x is equal to m, which I have assumed was not equal to 0. So if my derivative can never be equal to 0, then I could not have possibly had two roots. Therefore, this has at most one root. I'll do this again with n equals 2. N equals 2. Then my polynomial is a quadratic. I have ax squared plus bx plus c. And I'll suppose it has three roots, because we know that we can have polynomials, or quadratics, with two roots. Those are pretty easy to come across. But if there are more than two roots, then there are at least three, and I should be able to find three roots. We'll call it root 1, root 2, and root 3. But by Rolle's theorem, that means that there is a slope of 0 somewhere between each pair of roots. Meaning my derivative must be equal to 0 at least twice. But p prime of x is equal to 2ax plus b plus 0. But this is linear, which means it has degree 1. And I just showed that polynomials of degree 1 have at most one root. So there cannot be two roots for the derivative, which means there cannot be three roots for the original function. And I think this is what my induction step is going to look like. I'm going to try to take my derivative, I'm going to have something true about Rolle's theorem, and then I'm going to get some kind of a contradiction. So we'll do the induction step. We'll suppose polynomials of degree n have at most n roots, all for every n up to k. So I've verified it up to polynomials of degree k. So let's suppose we have a polynomial of degree k plus 1. Just so we have a different letter, I'm going to use a q. Q is of degree k plus 1. Which means I could write q of x like this. That's a g. I'll have a constant term, a0, plus a linear term, a1x, plus a2x squared, plus up dot dot, a sub k, x to the k, plus a sub k plus 1, x to the k plus 1. I don't particularly care what these coefficients are, just that they're there. And I want to show that q of x has at most k plus 1 roots, so I'll do what I did before. Suppose q of x has more than k plus 1 roots. Then q of x has at least k plus 2 roots. And I should be able to write them out all in a line, so I'll have root 1, root 2, root 2, root 3, dot, 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 root k plus 1, and root k plus 2. Then by Rolle's theorem, in between each pair of these, I'm going to be able to find a slope of 0. One between 1 and 2, one between 2 and 3, one between 3 and 4, all the way up until I get to the end. One between k and k plus 1, and one between k plus 1 and k plus 2. So how many spots do I have with a slope of 0? Well, I've got 1, 2, 3, up to k and k plus 1. So by Rolle's theorem, q prime of x has at least k plus 1 roots. But, there's another big but here, q prime of x is equal to, we're calling the definition of q, is going to be 0 plus a1 plus 2 times a2x plus 3a3x squared plus all the way up until I get to ka sub k x to the k minus 1 plus k plus 1 a sub k plus 1 times x to the k, which means q prime of x is only of degree k. And by my induction hypothesis, what I assumed there was that every polynomial up to degree k had only up to k roots. So q prime of x has at most k roots. But it was supposed to have at least k plus 1, which is my contradiction. This is a contradiction again. Which means q of x must have at most k plus 1 roots. And that proves the fundamental theorem of algebra for us using Rolle's theorem. There are, of course, even more abstract examples where you can talk about pictures and tilings of things, but these are the ones relevant to calculus. I will add one problem on the exam, similar to how I did for the first, where I asked for an induction problem similar to one of these sums here, like when I did I squared. So be sure to give one of these a shot, and let me know if you have any questions.